Hello everyone, I am Philippe Hérail. I will be talking about our work with Arthur Bit-Monnot on learning operational models from demonstrations, mainly focusing on model parameterization and quality evaluation. So first, a bit of context. We are working with autonomous agents acting in a non-deterministic environment. They have to carry high-level activities and therefore have to balance between their long-term goals and their reaction to unexpected events. For that, we consider that the agents use hierarchical operational models together with an acting engine. Hierarchical operational models are HTN-like structures comprised of a set of abstract tasks that are refined down to primitive tasks using methods. These models encode how an agent may carry out some activity. Abstract tasks represent high-level behavior. They need to be refined down through the use of methods. These may contain post-conditions that are used to decide whether or not a task was successful. Methods determine how an abstract task is to be refined down. It does so with a set of subtasks and a set of preconditions that are used to determine whether the method is applicable in a given state or not. Primitive tasks simply represent the executable capabilities of the agent. Hierarchical operational models provide some benefits as they can balance between reactive and deliberative acting with the use of the acting engine, and also they allow to abstract frequent and local behavior due to their hierarchical nature. However, they also present some issues as they require expert knowledge to be designed and or updated, and it is also difficult to anticipate every reasonable situation that the agent may face. Therefore, we need to learn these models. For that, we want to learn them from demonstration traces to reduce the learning time, and of course, we want to learn sound and efficient operational models in order to help the agent achieve its goals, not hinder it. Our main contributions are a procedure to extract model parameters from a set of demonstration traces, as well as a procedure to evaluate some model with respect to a set of demonstration traces. Here is an example of a hierarchical operational model. As you can see, you have a top-level task, and you have your primitive task, here highlighted in orange. We have a lot of abstract tasks, including the top-level task, but they may appear anywhere in the hierarchy. And we also have some methods decomposing these abstract tasks into other abstract tasks down to primitive tasks. As we are learning from demonstrations, here are the demonstrations structures that we consider. We consider sequences of state and actions, as shown here, but we may have some non-primitive tasks in our demonstration traces, as shown in this second trace. To go from these traces to the models that I have shown before, we have devised the following approach. First, we need to generate a set of candidate model structure, then extract the parameters from the set of demonstrations for this structure, and then evaluate all our structures to get the best model out of this. The first part we left out of this work to focus on the second and third points, and we used the brute force approach as a placeholder. Graphically, this looks like that. We have our candidate model generation from the set of primitive actions and the initial vocabulary of tasks. From this structure, we extract the parameters using the demonstration traces and then get the best model out of this set. Now let's talk about model parameterization. When we have a base model like that, without any parameters, just generated from our first point in the previous procedure, you can see that we have top-level task arguments here in orange, we have primitive task arguments here in blue, and there is no overlap with them, and some methods don't even have parameters. Therefore, we need to extract them and unify them as much as possible. For that, we have devised the following procedure. Considering our model with methods, abstract tasks, and primitive tasks, we will group them in different sets. First, we will consider the set of all that is already parameterized, initialized with a primitive task, because we know their parameterizations. Then we get the set of all the elements that are ready to be processed, initialized with the methods that refine down to primitive tasks, and we group everything that remains in the remaining set. While we have elements that are still to be processed, we get one of them, we extract its parameters, and then we say that this element has been parameterized. Then, for all the remaining elements that need to be parameterized, we check if all their sub-elements now are parameterized. If so, we remove them from the remaining set, and we put them in the set of elements that are ready to process, and we repeat this process until nothing is left to be processed. And just as an overview, the parameterized procedure works by finding parameters that are unified to the same constants in every demonstration. Therefore, we can go from our original model that I've shown before to this new model, where, as you can see, parameters from the top level task are going down to the primitive tasks. Let's now talk about model quality evaluation. Our technique is based on the minimum description length principle, aiming to find a compromise between overfitting and underfitting model. This technique stems from information theories and views learning as compression, and as an equation in our case, we have this. This is simply the length of the description of the model, plus the demonstration set description length, knowing this model, and an alpha term to balance their relative importance. Going now to the length of the demonstration set, we have this equation. So what this means is that first we try and reconstruct all the demonstrations using our candidate model. Then we find all the choice points where an acting engine would have to choose between several methods. We find at each step the number of applicable methods, here, and we compute the logarithm, and then we sum all this and get the average over the whole demonstration set. As a conclusion, we can present some preliminary results. So first, our parameterization allows finding reasonable parameters mapping, which in turn allow to extract reasonable preconditions. And besides, our model quality evaluations favors balanced models that are not too generic nor overly specific. However, we need a more thorough evaluation, and for that we will integrate our new model with an acting engine to evaluate them more thoroughly. And we will develop a search procedure for candidate model structures to replace our brute force approach.